Might have a moderator, but there's no one here. So we might need to ask people to come in to start this session so that we don't fall too far behind. Yeah. And then, let's see, speakers, I think you can come up during the questions for Zeljko's talk. So no need to stand like lemons by the side of the stage. Zeljko's there. You can come up when we'll use this mic, so it's all fine. No, I think we can, when everyone's in, we'll just start, and then you can come up. It's all on the same slide deck, so everyone can hear this.
So then you got that.
Yeah. Okay, let's get started then. Thanks for joining us for this plenary session on observing strategy. What we're going to do in the next 90 minutes, I'll tell you a little bit about this approach we've been taking to studying the LSST observing strategy. Then we'll hear an update from Zeljko and the project SIMS team that have been providing the data on the cadence that we're using in our analyses. And then we have 7 highlights from our ongoing study covering a range of different science topics and focusing on the quantitative results that the community has been producing. And then at the end, if I remember, I'll invite you to the hack session this afternoon. Okay, let's see. Okay, so as you all know, the science with the LSST depends, in some cases, very sensitively on the observing strategy that we take with the facility. So, for example, there's a couple of plots here that are illustrating this. You see on the left, this is showing completeness in the detection of potentially hazardous asteroids. And for those, you need multiple visits per night. But you might think there could be some tension in such a plan with a science case that needs very uniform imaging across the whole sky over the campaign. So we need to understand how those two science cases are going to interact with each other. The way we do that is by using simulations of the LSST observing campaign. You've seen this before. We have an operation simulator written by the project SIMS team. And here's a sky map showing the achieved depth in the R band for what's known as the baseline cadence. That is the vanilla plan for the observing strategy of the LSST as realized by the OpSim. And you can see that it's doing a pretty good job of reaching uniform depth after 10 years. You can see other features like the galactic plane being filled in at lower numbers of visits and so on. Okay, so the baseline strategy is great. This year we've heard from the SIMS team that it does meet many, if not all, of the requirements in the science requirements document. But we can imagine that the science community might have aspirations beyond that SRD. And so it's interesting to us to ask, will the observing strategy as currently planned serve the science projects that we want to do with the data? So in this construction phase, we're already thinking like astronomers using LSST data. And it's similar in spirit to thinking about a proposal you might write for observing time, except we're interacting with a survey. So to optimize the LSST observing strategy, clearly that needs to be science-driven. We need to understand how well a given strategy will perform for us. So we can do this by actually testing simulations of the observing strategy against our own particular science goals. Okay, what does that mean to optimize the observing strategy? Well, first we have to evaluate the current baseline strategy, this baseline cadence. And the way we've been empowered to do that is through the project SIMS team's so-called metric analysis framework, which is a way to allow scientists to interact with the outputs of the operation simulator and do the kind of tests that we need to do. So how do we think about the evaluation of cadences, of observing strategies? Well, when you write an observing proposal, there's always a bottom line. You put it in italic text, and usually at the top, and it's of the form, if you give me this much time, I will be able to do this. And it's that this that we're trying to capture in something we might call a figure of merit. Now, that figure of merit are likely to depend on various features of the observing strategy that we can capture quantitatively in things that we might call diagnostics, that somehow summarize the observing pattern that the telescope follows and allow us to evaluate that pattern for how well it will enable us to achieve our figure of merit. So we have figures of merit and diagnostics as concepts. It turns out both of those things can be coded within the math using their metric classes. So when I use the word metric, I try and reserve it for this piece of code written in math. But more generally, we're interested in diagnostic metrics and figure of merit metrics. Okay, so this all sounds kind of abstract. Let's give you an example. Personally, I'm interested in using LSST to find hundreds of lensed quasars, strong gravitational lenses, and using those to measure distance in the universe so that we can understand something about how the expansion of the universe works. And so I know that I need each of those lenses to deliver something like 5% precision in distance, and that will be translated into the cosmological parameters. So a good figure of merit for me is the precision in the final dark energy parameters. Now, to calculate that is a lot of work. So a good proxy for that is something more like the mean precision in the time delays between these flickering light curves that I'm hoping to measure. So mean precision in time delay is my proxy for my figure of merit. So how well we can measure these time delays on a system-by-system basis will depend on the observing strategy. And in particular, we expect it to depend on the length of the season, and that will vary over the sky. We also expect it to depend on the gap, the inter-night gap, so the number of nights between successive observation sets. And also the campaign length. We know that 10-year light curves give more accurate time delays than 3-year light curves, for example. So those three are examples of diagnostics. They summarize the observing pattern so that we can make sense of it. So we did a project where we simulated, outside of the SIMS framework, we simulated thousands of lens quasars and did that in 5 different setups. Where each of those setups had a different mock observing pattern characterized by an inter-night gap, a season length, and a campaign length, so that we could understand how our ability to measure time delays related to those properties of the observing strategy. So what we did then was derived a simple model for how that dependence works. We can then take that simple model and code it into the math. So with Lynn Jones' help, we took the model from the paper and made 3 diagnostic metrics and 1 complex metric that depend on those metrics that tells me what's the expected mean precision on a measured time delay. And in fact, that's the map that you can see on the screen here. That's showing, answering the question, if there was a lens quasar at this point on the sky, what's the expectation value for the precision on the time delay there? Okay, so we're thinking along these lines. We have these concepts in mind, and we want to get to quantitative answers about how good a particular observing strategy would be for our science. We're working on this together. So we have formed a community that's interested in the LSST observing strategy, and the thing that is tying us together is a white paper, which is, you can think of it as a compendium of science cases like the one I just showed you. So each of those science cases are somewhat independent. They're actually organized into chapters by science theme, but they can be read independently. And the reason we're doing it together is so that we can share the experience of using the math and provide a good place for the project to come contact us. And the ultimate goal is to provide good information to the Science Advisory Committee for when they actually make decisions about how the scheduler will work. So we want them to be able to do the right thing. Okay, so this is an open source project. Everybody is welcome. It's very easy. You go to this website, find the issues, and just start typing, and that will generate a message to me and other people. At the moment, we have 85 people authoring this white paper, covering 30 science cases that have already been quantified one way or another, and there are more science cases speculated about in our future work sections. So I encourage you to come to that website and have a look at what we've been doing. Okay, so where are we with this white paper? Well, we envision it to be a living document. So its main purpose is to provide good feedback to the project, but it's also functioning as a community center, like I say. And that's important because as we go, we'll pick up new science cases with scientists that are interested but not as experienced in using the tools that we are. And so by joining this community, we hope that they can learn about how to do things and advance their analysis. But what that means is that this white paper will always have a set of science cases that are in a range of states of development. And so we've tried to bring that out a little bit in the highlights you'll see in a minute, that some science cases are more advanced than others. Okay, we have people that are, as well as using the white paper to track and share what they're doing, where they're up to, they're also starting to spin out journal papers from this analysis. So far, I think there are 2 papers that have come about from this interaction between the science collaborations and the project. So we're close to completing version 1, and we're hoping to post that to the archive, partly to advertise to the rest of the astronomy community that this is something that is happening and that there is a mechanism for joining in. But also to make sure that people who've been working hard on this are correctly accredited for the work they've done. So we're doing this. We need important LSST science cases to be represented quantitatively. And now I'll turn over to Zeljko, who can give us an update on, from the SIMS team about these different simulations. And then maybe we'll do a few questions together afterwards.
Okay.
All right.
Should I use this microphone?
I think so.
Good morning. This is just a brief update from the SIMS team. I'm Zeljko Ivezic, project scientist. The SIMS team was led by Andy Connolly until about 6 months ago, and then Lynn Jones took over because Andy was focusing on data management just like me over the last 6 months. So Lynn Jones just gave birth to a baby boy 2 days ago, so she's not here. Little Merlin. So I'll just give you a brief update. I have 10 minutes, so I can't go into any depth. So it's essentially a bunch of web links that you should follow if you want to learn more about OpSim, about math, about strategy for observing with LSST, different simulations we have, and so on. There is a nice summary talk that I gave to the Science Advisory Committee about a year ago. Here is the link. Then we had a year ago in Bremerton a meeting on observing strategy. You can find all the talks posted at this link. And if you want to learn more about OpSim, there is a single entry point here, and this talk will be available from the web pages for this meeting, so you can write them down, but you don't have to. So there is a lot of material that the OpSim, the simulations group, put together that you can follow to learn technical details. For example, what is OpSim? What does it do? How does it? Where does it stand? What's the development plan? And so on. So today I just want to report on a couple of important things that happened over the last year or so. We have a new baseline cadence. It's not official yet in sense of the change control board, but the package has been submitted to the change control board and recommended for adoption. So informally, it's the new baseline cadence. It's very similar to the old one, except it's better in some aspects. Now we have more than a dozen different ways of deploy LSST that we can study. And there is, I'll show you a link where to go to explore that. And then I'll just conclude with a slide that Andy gave me about the next few years of the development that is planned for OpSim. So the new run is called Minion 1016. These funny names are machine names plus the run number. That's how we keep track of them. The old one was OpSim 3.61, so that one will become deprecated. I think it was 2 years ago when we reported detailed study of OpSim 361. It had a number of I would say, minor problems. So we essentially know how we will deploy LSST. We should always remember that we have quite a good idea how to do it. But there is room for improvement at the 10% level of efficiency, and perhaps more if you look at the window function in time domain for getting variable phenomena on the sky. I think we can significantly improve it, and there are a bunch of ideas already proposed how to do it. And there were some bugs. There was 10th-year panic when you have to get certain number of observations in each filter per field, and then you come to the 10th year and you realize, uh-oh, I'm missing lots of observing in this field, and I have to change filters, and then it just goes crazy. So that was essentially a little bug in the code that was fixed. We still have some problems. We haven't implemented the sky brightness model that exists. The new model that Peter Joachim developed based on ESO sky model is finished, but it's not called by the code. That will be in the next generation. There is something called Western bias, where often we end up observing not close to the meridian, but close to the air mass limit towards west, and we'll fix that too in the next incarnation. So for all practical purposes, nothing significant strategic changed in minion 2016. It's similar to the previous cadences. We know we get roughly 2.5 million visits for 10-year survey. We know we have very good behavior of the slew time. It's just slightly longer than the minimum possible slew time, so it's all working pretty well. And if we had to go on the sky tomorrow, we could do it, but it wouldn't be perfect. We would not fully utilize the system. There is room for improvement, and that's what we aim to achieve over the next few years. These plots, they are produced automatically with a tool called Math, and you can find of the order few hundred plots and about 150 different metrics for each of the observing runs that we have if you follow the links that I provided earlier. Here is a list. It's a table from that white paper that Phil talked about. You can just go on GitHub, get the white paper. In chapter 2, you can find detailed analysis by the project, detailed discussion of these various modifications of the baseline cadence. I don't know if you can read from where you sit, but some of them explore different exposure times, some of them explore different sky coverage, some of them explore different ways to get solar system science out by having 2 visits, 3 visits, 4 visits per night. So we tried to start with baseline cadence and then depart along certain scientifically or technically interesting axes, and then we ran it through Math to look at all the metrics. Here is a good example of questions we are asking now in this process of optimization of the deployment of LSST. For example, our baseline cadence and SRD specify a survey of about 18,000 square degrees. And we can achieve a survey that covers 30,000 square degrees, that's on your left, with just slightly fewer visits. And if you look at various science metrics, for example, you ask, what is the number of resolved galaxies with which I can do weak lensing, one of our main science goals, and these two are practically identical. And so then you go science metric by science metric and you ask, which of these two is better, which one do you want? And so we play these games with not just one idea, but with multiple ideas, and that's where we now need community support, community help to ask questions that we cannot think of. Every science has numerous questions that can be asked, and we somehow need to summarize that collective knowledge and experience into one final number that we will use to rank these strategies and say, this is how we're going to start the LSST survey. And then perhaps then, after a year or two, we will change our mind or improve what we are doing. But that's the game we are playing right now. There are already a number of ideas that resulted from this process that started a year ago in Bremerton. There is this web page where you can enter your own ideas. And then Andy Connolly and myself go through these, and then we translate them into action items for the simulations team. It takes time. It's not instant gratification. It's not like you click on a button and you get math outputs immediately. It takes some time. Indeed, we haven't done some of these because they didn't easily fit in the development plan, which is summarized on this slide. That's my last slide. So this is a process that takes time. The team is not of infinite size, of course, and so we need to prioritize. And so that's the plan that Andy came up with. It involves project deliverables, it involves participation by the community, And we hope by the time of the first light, we will be ready to deploy optimal strategy. Again, all these links will be in this talk on the web, so you can follow them. And Phil and we will take questions now, and Andy is over there if you have more detailed questions about this plan.
All right. Oh. Yep.
So I'm one of the editors of one of the chapters, and so I've been trying out the process, and it's a gargantuan effort to get people to actually do this already, because it's unpaid work, so they can basically do the work, and then to some extent they're going to do more time. And so some of the feedback that I get back is people want to know more details about how are these metrics, how is the work then going to be evaluated to construct a plan for a system. And it's not clear to me.
Well, there are two parts to the answer. So one part is we will try to minimize unhappiness rather than to maximize happiness. We have multiple science goals. So we promise to the agencies we have these 4 science teams. So it is unlikely that we'll just drop one of these teams on the floor. We'll try to get as good a survey as we can to address all these 4 science goals. The ultimate decision process will involve community that will then channel their thoughts and priorities to the Science Advisory Committee, which will then tell us what they think, tell to project science team, and finally the ultimate authority is directors to decide that certain cadence is adapted or not. Now, technically speaking, for the metrics, we are still working on the process of how exactly you go. Every metric, ideally, you would have every metric defined from 0 to 1, and then the science outcome scales linearly with it. But how do you quantify science? And it's complicated, and we are still learning how to do it. And we made tremendous progress over the last year or 2. Now we have tools that, even though we cannot normalize all these metrics, but we can take large number of simulations, like 10, and we can just make tables and say, look, this one is red, this cadence really failed badly in this particular science case. We can't do that idea, we have to modify it. And there are many more details in chapter 2 in white paper.
But I think it would be very helpful to make this extremely transparent and very obvious to the people that are thinking what should be created to the cadence paper. What are the rules, what is the current plan to evaluate?
I think we do plan, there are some words in the white paper that we are unhappy with, and I think there is plan, you or Beth or me, or I forget who, we will improve that section, right?
I think we said on Monday that Michael might.
Michael, that's right.
So Fed, could you go to the GitHub page and find the issues and just write a note in one of those, in a new issue to Michael, that the introduction should really have a little section about this, I think.
Michael is in charge, consider it done.
Let's have at the back and then Brent.
So chapter 10 describes some additional interesting surveys. For example, a bright, short exposure time twilight survey. How will the project evaluate these kinds of ideas and go forward with them that are sort of in addition and perhaps increasing the scope of the project?
I guess that's again for me?
I think so, yeah.
There is actually a proposal to Project Science Team and Change Control Board to consider such survey by Chris Stubbs. I think that proposal is public document. We can identify it. If you have direct interest in this, we can make it available. So we are considering whether it is technically feasible and whether we can do it without significant increase in scope. We could gain a lot of useful data this way. And so that's something that we actively consider, and we haven't made a decision yet. And definitely once we have something firm to communicate, it will be communicated through usual channels.
And I guess it could even be simulated with OpSim and then evaluated with all the metrics we have in the usual way.
That's an excellent point. So in principle, it can be simulated with OpSim, and it was simulated with OpSim. But as I said, our sky brightness model is not good in the current implementation. It's good for dark sky, it's good for many things, but for this particular example of twilight sky, it can be off by several magnitudes. And the new sky brightness model performs well, but we have to call it from the OpSim. So next generation of simulations will have this effect in.
Okay, last one, Brant.
So there's a chapter on W first, and that chapter presents some potentially quite dramatic changes to the baseline observing strategy. If you implemented those changes in the future, there would be quite a divergence from what's presented. So what is the likelihood, or how are those decisions going to be made? Is that happening just based on metric analysis, or is it more of a project level decision? How do you plan on it?
It's at multiple levels. So if it's increasing technical scope of the project, if it would result in significant scope changes, it's unlikely to happen. But in this example, it's basically just changing the way you would deploy LSST. So basically, it's a matter of politics and science outcome. And so the input would come from the project level people, simulations, who would say that would be the result of this idea, but then we would have to involve, in this case, I think not just project, but SIC, possibly agencies, it's a major thing. Then collaboration with W first, it's a complicated thing.
But you can see how that discussion will go better if there are quantitative results on the science from the map side. So again, I guess simulating it would be
Absolutely.
an important part of the process.
I think there are simulations that would be useful in it.
It's on the list of proposed simulations, yes. So on the order of a year or so, year and a half, we might have such a simulation.
Okay, great. So at this point, I'd like to invite the 7 highlight speakers to come up and form a lineup because we're on a tight schedule here. So maybe if you could come and join Humna over on this side, it will be easy for you to come up to the podium when it's your turn. You can do it on the right time, I guess. So let's see. Humna, come on up. So Humna, I'll explain to you how this is going to go, and then hopefully all the other speakers will listen as well. So you remember it's 5 minutes talking time, and then we'll have 3 minutes for 1 or maybe 2 if they're quick questions. And the duck will quack when the 5 minutes is up. So, and I'll just be here as well to help. And then it's left and right buttons to advance the slides. Okay.
Hi everyone, I'm Humna. I'm a graduate student at Rutgers University, and I've been working with Eric and quite a few other people on looking at what the LSST observing strategy implies for large-scale structure studies. So to start off, we look at the R-band co-added depth, which is basically a depth after the 10-year survey. Once we know about the artifacts that are induced in the co-added depth, we look at the artificial structure that those artifacts induce and what that means for the LSS systematics that we want to look at. So the analysis tools that we consider, we have the OpSim simulator output. We have mock catalogs to convert depth fluctuations to galaxy counts. And we use heel picks to tile the sky with equal area pixels. That basically allows us to look at small scale fluctuations and look at what that means for LSS systematics. So we all know that LSST field of view is circular, and the baseline cadence strategy tiles the sky with hexagons. So if we have fixed telescope pointings, there are overlapping regions between the hexagons that are observed a lot more than the non-overlapping regions. This leads to a very strong non-uniformity in the co-added depth, and this is something that we know about. So in order to mitigate that effect, we look at implementing dithers, which are basically telescope pointing offsets that are on the scale of the field of view itself, to capture the range of time scales and the geometries of the dithers. We look at 3 different time scales: per season, per night, per visit, different geometries, random, repulsive random, hexagon, and spiral, and we basically simulate what the survey is going to look like with those. So these are the results with the co-added depth. You can see the no dither, the under the survey is very strongly non-uniform. You can't really see the honeycomb as clearly, but those are because of the honeycomb pattern is because of the overlapping regions.
So is that the end of 10 years?
Yes. And if you come look at all the dither surveys, you do not see that honeycomb pattern anymore. And this basically tells us that dithering really, really helps the artifacts in the quadrant depth. Okay. So once we know that, we basically propagated the fluctuations in the depth to fluctuations in the galaxy counts. The LSS systematics that we focus on is the power spectrum. Because the observing strategy induces artificial structure, it induces a bias in our measurement of the power spectrum, and the uncertainty in that bias is a limiting factor for us to correct for that bias. Also, because the power spectrum is a signal, there is an inherent statistical uncertainty that is associated with it. So our figure of merit basically is to reduce the uncertainty because of the observing strategy bias. And that's what we want. We construct the field of merit. It's the ratio of what would be the perfect information and the one with the OS bias itself. And ideally, we want it to be as close to 1 as possible. So we simulated the 10-year survey. We looked at the bias uncertainties, because we are constrained on time, just look at the blue curve is for the gold sample. As you can see, under the survey leads to very large OS bias uncertainties, which is a really big problem. In comparison, the dither strategies do not. Repulsive random, even per season dithers are really, really effective. On the right there, here, you see the sequential hex. That is an example of that's a very important example because it hints at the sensitivity of the time scale and a dither combination. And even though we are dithering so often, the OS bias uncertainties they're not minimized. So this is something that we know about. We know that dithering really, really helps, at least over the 10-year survey. Looking at the 1-year survey, this is basically what happens after the first year. You can see no dither is still doing really poorly, but there are some dither strategies which are doing as bad as no dither itself. Even the best dither strategies, which is repulsive random, is not really minimizing the OS bias uncertainty to be below the minimum statistical 4. It's getting close, but not where we would like. And you can look at the field of merit values. They're not really close to 1. Well, some of them, 0.7, 0.8. So to summarize, we basically looked at how, we know that dithering induces strong artifacts. They are particularly harmful for the 10-year survey for LSS systematics, and we will most certainly need correction methods after the 10-year survey if we don't dither at all. Other future things to look at is interaction with other probes, because I'm almost done. Other probes have to see which strategy works best for them, what's best for their systematics, and there's a very tiny, quick application of our analysis to emulate what the galaxy sample is going to look like as a function of redshift and magnitude. Okay, thank you.
All right.
Any questions?
Okay, so yeah, we have a couple of minutes for questions about the analysis, I think, rather than the science.
Yes.
Michael.
So can you go back one slide, please? So what we're looking at and what you're worried about is that peak at around 130. That's really that's the thing. Do you have an intuition why it's still there so strongly in various of these?
Yeah.
And why it goes away after 10 years?
Yeah. So the thing is, those dither strategies do lead to hexagonal honeycomb-like structure after 1 year, but over 10 years, sequential hex actually gets rid of some of it. You can see horizontal striping in some, so that's leading to that kind of structure. But the repulsive random does not lead to any very strong structure even after 10 years. That sort of gives an intuition of we want to minimize the structure that is actually present after 1 year and after 10 years. Right.
And
So is it one of these that's in the baseline minion?
Baseline minion has sequential hex field per night, I think. So that's why we were like, no. Yeah. Yeah, okay.
so Humna was telling me that she's quite excited about now taking this analysis and applying it to some of the other databases that we have. So that should be an interesting thing to see this afternoon at the hack session.
Okay.
All right, let's thank Humna again.
Hi, I'm Eric Bellm. I'm one of the co-editors along with Fed Bianco for the Transients chapter of the Observing Strategy white paper. The transient science is particularly sensitive to the choice of observing strategy And so we're very interested in this exercise to help optimize it. I think it's useful to remind ourselves of the problem we're facing, which is using all of this heavy infrastructure we're building of the alert streams and the brokers to identify intrinsically rare events in this massive stream in real time so that we can trigger follow-up of using resources that are themselves scarce and valuable. And so the LSST data itself in its cadence, it has a particularly strong lever arm in allowing us or preventing us from finding these rare events. In particular, again, the sequence of events as well as potentially color information. So to give a concrete example, you can imagine LSST finds a new detection of a source that's never been seen before at 23rd magnitude. It's on the outskirts of a local galaxy. So the question is this the youngest supernova ever discovered that LSST is seeing for the first time because it's so much deeper? Or is it a supernova 1A in a faraway background galaxy that we're just seeing near peak, and it's very uninteresting? And so if you have 30-meter spectroscopy time, 1 TOO a year, are you going to trigger that on a single data point? Probably not. And so other contextual information from LSST, upper limits, another detection later in the night, can really help clarify those two cases. So young transients in particular are extremely valuable scientifically. Supernova, there are many sort of core aspects about the progenitors that we can only really learn about if we identify them young, in the first sort of day or so after they explode. Similarly, fast fading events like gamma ray bursts, we can learn about their jet structure and composition, as well as try to find, with LSST's depths, the GRBs from the very first stars at high redshift. And so the figure of merit that we sort of care about here scientifically is, how many of these young events can we discover sort of less than 1 day after they explode? And I say discovered because it's not enough just to have it in the database. We have to recognize it in time to trigger all that follow-up and get the intensive observation follow-up campaigns that these rare events deserve. So we have some help intrinsically. Many of these explosive transients evolve quickly when they're young, most quickly. So on the left are light curves of a representative sample of real supernovas, cataclysmic variables, as well as some theoretically predicted events. And you can see that they rise very quickly in their early lifetime. And so on the right, there's a plot of the slope in magnitudes per day versus time. So you can use the rise time and the evolution to distinguish young events from old events. And also they tend to be bluer in color. So turning to the simulated cadences, the challenge is that the current simulated cadences aren't really adequate for distinguishing young and old events. We're looking using a sort of diagnostic metric, the gap between exposures in a night. We see that virtually all exposures with LSST are currently scheduled less than 30 minutes apart. And of course this is for asteroids, but it's very poor for distinguishing young transients because they don't evolve enough in 30 minutes to be able to distinguish them at sort of characteristic photometric precision. And so we really need a longer baseline to be able to distinguish young and old events. Similarly, for gamma ray burst afterglows, if you put in realistic light curve shapes, we're only finding a very small fraction, potentially, of the events that LSST can see because of that sort of slow sampling rate. So just to look at some potential ideas that would improve LSST for transient discovery, we've talked a lot about rolling cadences. If you can get that previous night upper limit, that helps a lot in distinguishing young events from ones that are several days old. Similarly, more visits per night separated by longer baselines, 2 or more hours, will allow us to distinguish those fast, young, rising events from slower events near peak. And also contemporaneous color information has potential as a diagnostic. Where we're going from here, what we really need to do is to do real population estimates with realistic light curves. So we'll be working on some Monte Carlo approaches in the hack session today, and so if you're interested, I hope you'll join us. Thanks.
All right. All right, so a few minutes for questions on the analysis for Eric. Yeah.
A totally dim question, Eric. How many of these things will really mess up other people's cadences?
I don't know, and I think that's why we need to do the simulations to find out. I think there's a lot of experimentation we can. Exactly, yeah, and there are exactly those technical limitations that we have to confront. I think the simulations team is very creative, and you know, as they roll out these rolling cadences, we'll learn more.
Tony?
It would be useful to distinguish between deep drilling fields and the regular survey.
Yeah, I absolutely agree that the deep drilling fields are interesting. I think it's premature to say whether or not the, whether any science case belongs in the deep drilling versus the main survey. As well, one of the challenges right now with the deep drilling fields, as I understand, is they're mostly implemented as sit and stare changing filters, which doesn't really help with that fast rising because there's not enough time baseline. But we can certainly consider, I hope we'll talk about in this afternoon's session, other ideas.
Michael, you had a question?
So there is at least a mock-up of rolling cadence among the existing OpSim apples. Have you taken a look at them and see how much better those are?
That just rolled out sort of, in the last month or so, and we haven't run it through yet, but yes, I agree that's a high priority for us.
I guess one reason why Eric and the Transients group are interested in the populations is to be able to start prodding different patches of the sky. So look at the subset that actually would be in the deep drilling fields or actually in the rolling cadence area. So that's why the hack session should be good for that. Okay, let's thank Eric again.
All right, so this is going to be a very large category for anything that I'm going to call stellar variability. And so again, this is going to come into an issue of all sorts of time domains, questions of cadence. But to sort of explain what I mean when I'm saying stellar variability here, I'm talking about two very broad categories. One is intrinsic variability, anything that is the star itself changing. So flare stars, novae, any sort of pulsating star, something where the star itself is changing. And then anything that's an extrinsic variability. So eclipsing binaries, transiting or microlensing planets, circumstellar disks, anything that's beyond the surface of the star and is still having an effect. And so that's a very, very large category of a whole lot of fairly unrelated things aside from the fact that you can observe these by watching a star change. And this is also including both periodic and non-periodic variability. So this is a very, very big category with a lot of very different things in them. And so to sort of take a look at addressing that, I'm going to just look at a brief case study with dwarf novae, and really using this to highlight the diagnostic metric that was produced for this. And so the idea here was trying to figure out if we can roughly characterize that you have something like a dwarf novae where you have a baseline luminosity and occasionally it's brightening. And so what really would be the minimum to notice that this is actually going on? And this can work for anything that you have a brightness or dimming going on in a star. So in this case for a dwarf novae, I'm using SS Cygni as an example. And so the light curve you're seeing there is from AAVSO. And most importantly, this is not a periodic event. So this is looking at how can you detect that one of those brightenings is happening. And so to try to set up a metric that can actually handle this, and this came out of the Phoenix meeting, the basic idea was that you would really need your first observation that is during the event, so this is the middle vertical line, and then you would want to have one observation before the event so that you can somewhat constrain when it happened, and a second observation, a third observation at the end of that, which is confirming that your signal that this has brightened or dimmed is actually a real thing. And so this isn't looking at, and so for this metric, this isn't putting light curves in and seeing what we're observing. This is simply how many times for a given point in the sky do you have 3 observations that fit these criteria. And so these can be tuned for the specific science case we're curious about. And so with this idea of looking for dwarf novae like SS Cygni, we get something like this. And this is using one of the older operation simulations. And so if you can see them, there's a couple small white squares that show up right in here in the middle, and those are the signs that we have a couple deep drilling fields in there. And so in this case, the requirements was that we needed 9 to 11-day intervals between the first and the second observation, between the second and the third observation. And those are parameters that can be adjusted for any other source of variability that this same structure would work for, where you're looking just for that it's changed in brightness somehow. And so we roughly see deep drilling fields are very useful. Northern ecliptic spur actually is more useful than the regular part of the survey. And that this really can be adjusted to sort of be used on other sources of variability. And sort of as a future thing, this would also really need to be incorporated to get to that sort of figure of merit that's giving us an idea of the science. We'd need ways to incorporate, for example, the number of stars in a given region. Since it doesn't really matter if the cadence is great, if we don't expect there to be any of the kinds of stars we're looking for there. So there's more to be done with this to get to these final figures of merit. But we've got a couple of these building blocks of a couple metrics like this one that are designed with this broad goal of being usable for variable stellar sources of one kind or another, either periodic or non-periodic. So you can see a paper that I had come out the start of this year, which put a few of these metrics out there, including this one. And I'm still working to try to get at least these diagnostic metrics. And then the final challenge really is, how do we build from these diagnostic metrics to actually get these figures of merit that will tell us exactly or approximately how well we're actually doing the science that we want.
All right, thanks, Mike. All right, questions for Mike? Yeah, Virginia.
Are our core stars on your visual screen?
Could you repeat that?
Are Arcoma Borealis variables one of your categories? They're the ones that hold on like this and take something and come back and become 7.
I think it should be applicable to them. I have not attempted to do that yet. I am entirely welcome to anyone that wants to recommend stellar variability to look at. Personally, I deal with transiting planets, so I care about periodic and totally small signals. So, but a lot of the same kinds of tools apply to a lot. Yeah. So I think it should be just changing the parameters of the metric, and it should be able to be applicable to whatever you want if it's that same kind of rough signal.
So when you look in the white paper, you'll see that, particularly in transients and variables, those chapters, there's been a lot of work put in on this kind of building block diagnostic metric that can be used for many different science cases. And the hope is that when we advertise the paper more widely, we find astronomers who really care about certain objects that can come and join the community and use the tools that Mike and others have been putting together.
Yeah, the metric is up on GitHub. Please give it a shot.
All right, so let's thank Mike again and see you there.
Okay, good morning, everyone. I'm David Trilling. I'm going to very briefly tell you about analyzing the OpSim runs and the cadence for the science of solar system projects. There's a lot of things in the solar system, as you all know. For this brief presentation, I just am going to choose the case study of studying near-Earth objects, which I also will call NEOs. You'll see it in the top bullet there, NEO, near-Earth object. I picked that one because for solar system science, it's the hardest thing that LSST is going to do, and so if we can succeed for NEOs, then we can probably succeed for other things in the solar system. There's two reasons you might care about NEOs. One is to understand the compositions of bodies in near-Earth space, and the second is because sometimes those things hit the Earth and we'd like to know about them. And in particular, the thing that we would like to know is how well do we know the orbit of an object. of an NEO. How well you know the orbit tells you how well, with what confidence can you say this will or will not impact the Earth. Okay, so things we might want to know, this is obviously not the entire list. Things we might want to know for a given cadence is how many NEOs will be discovered, what's the completeness as a function of size, how well do we know the orbit. So let me just step through those really quickly. Here I'm showing on the bottom axis years into the survey, so a 10-year end of survey is all the way on the right side, and the vertical axis is completeness. And this blue line shows NEOs larger than 140 meters, which is kind of a benchmark number that I'll use several times today. So obviously you can see towards the beginning of the survey, the completeness is low, it's 25% or something, and after 10 years, the completeness is something like 60+%. Okay. Here's another one I want to show you. On the bottom axis is this crazy unit that I don't want to tell you what it means, but let me just call your attention. It's basically size. Here's 140 meters, and here's 1 kilometer. So big objects over here on the left and small objects over here on the right. Okay, and then the vertical axis here is what we've got is median observational arc in years. And what that means is the amount of time between the first time LSST saw that object and the last time LSST saw that object. And basically, the longer arc you have, the better you know the orbit. So the top of this plot means I know that orbit really well, and the bottom of the plot means I don't know the orbit very well. Okay, so obviously we want to know the orbits well. Pay attention just to the blue line, which is the NEOs, and you can see that over here on the big side, on the left side of your plot, I know the orbits very well. Those are big objects, I know those orbits very well. They have a long observational arc. On the far right side, those are the very smallest NEOs. I don't know the orbits very well because I have just a small observational arc. It's just part of 1 year that I see this and then I never see it again. And okay, so there's a turnover around 1 kilometer, and for 140 meters, which again is this kind of benchmark size, okay, it's about a 4-year median observational arc. That's actually pretty good. It's not the sciencer that I want you to take away from this, but rather the fact that we can make these kind of estimates based for any OpSim run. We have simulated objects, we can put them through the OpSim run, and then we could say, oh, this is what we see for the NEOs as a function of size. Okay, here's my last plot. Phil wanted me to emphasize that this is a figure of merit, so I labeled it here, figure of merit.
Thank you.
Okay, good. So on the bottom axis, again, is that same unit of size, and again, here's 140 meters, and here's 1 kilometer, so big is on the left side for you. And then this is completeness. And there's 5 different colored lines here, and each of these colored lines represents a different OpSim run. And they were in the table that Zeljko showed that had 20 lines in blue font. Those are all 5 of these are 5 out of those 20, and I don't remember what the names of them are. But you can see that they're slightly, they're tweaks on the same idea for NEOs. Okay, 3 pairs and 15 nights, that's a requirement in order to identify that object. Or maybe it's 3 pairs and 30 nights, or 4 pairs and 20 nights, whatever. These are different flavors that we're going to try and say, well, which of these is going to be the most effective for this science, and of course for your science as well. Okay, so here's my 5 curves, and you can see that at 140 meters, the completeness, sorry, that's what's on this vertical axis, completeness. Well, it's sort of like 50% for all of them, but in fact, the purple line is more like 30% at 140 meters, and whatever these colors are at the top is more like 60% at 140 meters. So there is a difference here that is worth noting. And again, just to emphasize that for any given run of OpSim, I can tell you, okay, what's the completeness as a function of size. Okay, lots of parallel examples for other parts of the solar system. Here's the conclusions, 3 easy points. Number 1, tools exist to measure some of these success rates. Number 2, different requirements can give different success rates, and that's good to know. And the third is that some aspects that I didn't show you are less straightforward to calculate, and these are ones we haven't really implemented yet, and there's some more modeling and maybe, in fact, some more thought that's needed before we can put those in. Thank you.
All right, time for a question or two for David. Chris.
So in the last few months, there were some papers from a
proof, I guess, on real-life people who wanted to satellite-based near-Earth orbit searches. And they had curves there for LSST. Sort of the point of it was if you make them work together, things are great. But my reading of it was they were trying to point out, how good they were in LSST out of the clear. I was just curious, are your numbers consistent for LSST with the things that are in those papers, or is it the press a lot?
I don't know the answer to that. I could know the answer. I mean, we have all these answers, and that paper has been published. I don't remember. They clearly had an agenda behind that paper, a message they were trying to present. And I don't know the details of which simulation and which expectation for LSST they used and all that. I don't know, is the answer.
So I'd like to say one reason why I did ask David to emphasize that this was a figure of merit is that it's hard work to calculate figures of merit. And this is something we've seen over the last year with the community. There's typically a lot of simulations involved outside of OpSim to do it. So every time you see figure of merit, it's a little cause for celebration. So congratulations, figure of merit. Okay, let's thank David again. Let's see. So,
okay, so I'll be talking about supernovae, science cases that use supernovae as distance indicators. And on the right are cases that have been proposed and are tied to the large sky survey area of LSST. But I'll be talking about constraining dark energy using supernovae at a range of redshifts. Because that's what we have in the white paper at the moment. So the question is, what kind of sky coverage is important? And how do we think about this in terms of the deep drilling fields and the WFD? So this is a plot which shows the current state of art in supernova cosmology. All the data was taken before 2008. And the places where LSST will improve is largely by providing much larger numbers of supernovae at all redshift bins. So this is a numbers game, doesn't matter where they come from. The second point to note is this area. The low redshift sample is completely homogeneous and taken from assorted samples, and this leads to lots of problems. And it would be good to get an LSST pipeline delivered low-Z sample. So the schematic way to think about this, I think, is since volume increases with redshift, high redshift will largely be deep drilling fields. If we can get anything else, great, but at least that should work. And at low redshift, there should be support from WFD, which means that at high redshift, we care about cadence as well as detection. That's going to be the limiting thing. Low redshift, mostly cadence. And so we should evaluate this figure of merit over all sky, but different redshift slice information would be important. And so we think about this in 3 steps: detecting supernovae, classifying whether it's a type 1a supernovae or type 2, and then characterization, by which I really mean obtaining distances from the light curve. And so what we'll need is a composite of these 3 metrics, and that would be a coherent product, by which I mean that the same supernova should have, so here, for example, the same supernova is good for all these 3 steps, whereas here, different supernovae are good for each of these steps, and that's not good. So we need a coherent product there. So the metric prescription that we tried to follow was we took a single supernova light curve, very standard light curve, and repeated it over time, and tried out a detection FOM where we basically look at whether it has at least one 5 sigma observation. Classification, we do not have a metric, and the reason is that doing this kind of small simulation, small population, is very hard to answer questions about ensembles like you need to for classification. So this kind of an approach will not work. Characterization, what we do is try to fit these light curve models, and the FOM is the sum of the inverse variances of the estimated distance modulus. So that can be thought of as the effective number of supernovae contributing to your dark energy equation of state constraints. So I'll go through one example, which is the detection. It's the simplest metric that we talked about. And you can see that at low redshifts, well, this is 0.5, it does pretty well. High redshifts, 0.8, not so much. But that's okay. As I said, you don't need the entire sky. But you don't actually see the deep drilling fields come out either. And that's because the deep drilling fields, the single visit depth is the same as WFD. So, okay, and that's important because at these redshifts, you will expect the deep drilling field to give you decent light curves. And so if we don't detect them, that would be a problem. So we need to do a more careful study there. So these are the conclusions that I wanted to leave you with. Some of these are sort of our answers to some of the questions that were raised. That's it.
All right. Thanks, Rahul. All right, so while you digest Rahul's last slide, do we have any questions? Fed?
So I think for this chapter, it's really, and for the chapter, the classification actually touched upon is really good as usual. We really had to design methods for that.
Yeah.
And also, I want to point out that it's not just about splitting the supernovae type 1A from supernovae.
That's true.
We need to start digging into
Yes.
but that we now know that there is supernovae type.
So we need to actually multiply the supernova metrics with the transient metrics that you guys have.
Yeah, and we, there is some effort including breakout sessions where they are focused on trying to think about that.
Any other questions for Rahul? Yeah, Jongi.
Hi, this is Jung Hiro. I'm working with Rahul about this. And I want to just add about our rolling cadence. That's important. So our goal is to generate a number of sampling. We increase factor of 3. So usually at current wide survey, we'll get just 3 and 4 points per band. But by doing this new rolling cadence, we can get like 9 points per band. So by doing this, we can really have a high quality supernova light curve from the wild field survey. That's our main goal. So by doing this, we can, for 2 months, we might be biased to cover one area and higher depths. But over the year, we can have same data as the baseline rolling cadence. So we can still remain uniform survey and same depths. So, but for supernova science, it will be really great. We can discover more supernovae and high quality light curves.
That's great. So in the discussions between this observing strategy community, we've heard statements like Jongi's throughout actually about how interesting it would be to investigate rolling cadence. And in fact, Kem Cook was telling me yesterday that in the new release of the OpSim code, now the SOX scheduler code, it should be much better at implementing rolling cadence. And so throughout this year, we should be able to do some more interesting tests of rolling cadence concepts, which I think will be good for many in the transient community. Okay, let's thank Rahul again. Right.
Sure.
Yeah.
Hey, well, good afternoon, everybody. Hope you can all hear me. I'm Will Clarkson at University of Michigan, Dearborn.
and along with Kathy Vivas, I'm one of the 2 chapter editors of the Milky Way chapter for the white paper. So there's a huge diversity of science cases that we've had input on from the community. I'm showing a couple of example cases up here. The column on the right, the mostly latitude agnostic or objects falling in the wide, fast, deep, those are quite well developed in the science book already. The material on the left, these cases that are led by stellar density, if you want some population but you know it's going to follow where most of the stars are, or if you have a science case where the inner plane is the place to be, that's a little bit less well developed. That's what we've partly focused on so far. So as well as the 2 sort of areas of the sky you can think of we might want to look at, there's sort of 2 broad levels to the kind of figures of merit that our collaborators want to know. For example, if you want to look at the next galactic supernova, of which there may only be of order 1 in the next 10 years perhaps, the figure of merit for that could be relatively easy to state. What fraction of events like this do we detect? But for much of the other science, it's much more population-based. For example, if you want to know what the brown dwarf mass function is in the solar neighborhood, we have to somehow simulate a population, all the different OpSim runs, come up with an uncertainty in the mass function, detecting crescent black hole binaries, for example. It'd be nice to know how many we detect, but even better, it'd be good to know what the population error actually is. So there's been some effort to follow those up. Now, for the density-led or inner Milky Way plane-dominated cases, for figures of merit, in some sense, it's easy because we know the answer before we begin. I think it's still true that there's only 2 of the OpSim runs that do anything in the inner plane after the first 200 days or so of the survey. And so for many of the cases, there are these 2 dominant effects that really lead what you can do. So this figure here from the white paper chapter 4 shows a couple of spatial maps. These are both in galactic coordinates. The one at the top shows the total time duration that the baseline survey provides to different regions, and it's color-coded by duration. The blue is less than about 200 days. So the southern celestial pole and the inner plane don't have as good coverage as everywhere else. And then the bottom one shows you the stellar density, stars per square arc second, brighter than 27.5 magnitude. So we can already say, if you have a science case where it follows the stellar density, or you need to have coverage beyond the first 7 or 8 months, we know the first order where this would be good and where this would be bad. So this is the glass half full viewpoint. This is a nice sort of training ground for your figures of merit, because they should give you an answer that your science cases in here should be disadvantaged. So there's sort of 2 aspects. One is we want to know sort of what questions to ask. If we want to ask the OpSim team to simulate different kinds of strategy, let's say inner plane but no U-band, for example, what do we ask? And second, how does this fit in with your science? So the one sort of test case figure of merit we've developed is to look for something that varies spectacularly and slowly, but for which we think it might just follow the density of stars in the galaxy. So this is sort of a density-weighted average of the fraction of variables detected from a certain class, supplied to us from our collaborators in the Transients variables group. And on the left, you can see this is a spatial map of the sort of the top part of this figure here over the sky. And for minion 1016, the baseline, it gets some, but not very many of the events in the plane because it avoids that area. For this OpSim run that extends wide, fast, deep to the plane, so that takes about 5% of the images from elsewhere, applies it to the plane. If you just take this sum over the sight lines, you can see quantitatively we do a much better job with a simple bright variability just over the whole sky. If it goes off somewhere in the sky, but it follows the density, then the wide, fast, deep extended to the plane will do a better job of finding it. So we have this in the chapter to kind of sort of provoke the community to think of ways in which your science might actually work for this as well. So in addition to this, there's a few science areas that have been, I think people have been talking about for a while, but the actual translation of that into the SIMS math framework has not been so straightforward. So One of the things I want to do soon, thank you, is to develop that in some more detail. This example shows you on the left this spectacular slow microlensing curve from Ogle. I want to show, the point I want to make at the bottom there is that that's a 3,000 daytime baseline. So if you want to know, for example, the compact object mass function from slow microlensing, something like LSST should be able to do this very, very well. And so I'm going to be having an unconference this evening at 6:30. I'll be at the Murphy rooms for those microlensing experts who want to help with developing more metrics based on this. I've run out of time, so I'll just skip to the conclusions. So at the moment we have a few example figures of merit run on a few OpSim runs. There's a few more that are in development. Colin Slater is leading the star-galaxy separation part. There are some, Chris Britt at MSU is leading the quiescent X-ray binary work. But we still need input from the project and the community experts everywhere. One output from this process of comparing the baseline and the two other OpSim runs that do the inner plane is how do we know a bit better what we need to ask for the inner Milky Way? For example, since this is not part of wide, fast, deep, can we do shorter exposures so we don't waste exposure time pushing beneath the Crowding limit? What about the Twilight survey? How does that fit into this? One question I would ask of my colleagues in the other white paper chapters is if you could please include the Astro LSST 01-1004 OpSim run. That's the one that extends wide, fast, deep to the plane. If you can include that in your figure of merit calculations, that would help us know how much we're stealing from you if we do the plane observations. My prejudice is that for most of the science it would just be incremental, but for plane science it would be transformative. So please bear that in mind. Right. And I think somewhat obviously we still need implementation of the other figures of merit in the chapter. So I've gone way over, so I'll stop talking. And thanks for your attention.
All right, I think we do have time for a question. Yeah, Michael.
So go back to any of the plots that show the sky coverage. The ones that showed it. That's one of those. So there's this spur of the galactic plane north of the equator, which always seems to me a bit artificial. How much do you guys care about that specific spur? Can we get rid of it from your point of view?
I don't have an answer for that question yet. In this particular case, you would chop off a piece of the plane that maybe isn't so bad, but I don't have an answer to that question yet.
I mean, is it a particularly interesting part of the plane? Let me ask you that.
Waving my hands, I don't think so, but it does depend on the output of the figures of merit for all the science cases. You're asking if it's worth...
Fair enough. You can make that argument about anyway.
I think
it's worth making.
Hopefully that'll come out of the process, right? Like if there's a science case that really does need that part of the plane, it might be worth stretching LSST to get that, but I have no answer to that question just yet.
So these are very interesting points because maybe you can see that as this process continues towards first light, you can imagine the science cases acquiring more and more metrics, some of which are sort of defensive in nature, right? That if the observing strategy is proposed to change, can we still cope? Like, can we still detect the objects that we know we can measure? All right, let's thank Will again.
All right. Hello, I'm Josh Myers. I'm here to present the observing strategy for weak lensing. So like other cases of static science, like the large-scale structure Humna showed us earlier, weak lensing cares about uniformity of the survey. Maybe uniquely to weak lensing, however, we especially care about the uniformity of the rotation angles that are used to observe any given part of the sky. So for instance, you can imagine that some systematics in shape measurement could be locked to the focal plane of the camera and introduce systematics that, say, extend the shape of a galaxy in the camera up direction. To help mitigate those, though, one thing you can do is when you return to that galaxy later in the survey, just rotate the camera 90 degrees so that systematic goes in the other direction, and at least to first order cancels. And I should mention that this isn't just pie in the sky. You know, in effect, like the anisotropic part of the brighter fatter effect could introduce exactly this type of systematic. So to look at the impact of rotation angles using math, we had to come up with a statistic that did a couple of things. So one, it had to measure the uniformity of the angles, and two, it had to know that 0 degrees and 360 degrees actually mean the same thing. You can't just use a simple RMS, for instance. So the metric we developed is this angular spread metric, and that the way that works is you take your set of angles you want to measure the distribution of, map them onto the unit circle, and find the two-dimensional mean of all those points. And then the distance of that mean from the unit circle is your metric. So this ranges then between 0 and 1. If all of the angles are the same, you get a metric that's 0, so 0 uniformity. If the angles are more spread out, then you get 1. And then finally, there's one additional caveat for shape measurement, which is that we don't actually care about the 360-degree periodicity of angles. 0 and 180 actually give you the same systematic and shape measurement. So to account for that, we just take all the angles from OpSim, double them, so anything that was separated by 90 degrees is now separated by 180 degrees, and use those doubled angles in the metric. So here's the results for what's currently in minion 1016 specifically applied to the rot sky pause, which is the angle between camera up and north on the sky. And I should mention that OpSim currently only has rotation of the camera implemented just to track the sky, since it's an altitude azimuth telescope. You have to engage the rotator during an exposure. And in a couple other cases, like you have to respect cable wraps, and you have to bring the rotator to home position in order to execute a filter change. So those are the only things affecting the rotator position in this current version of OpSim. And you can see we do pretty well already, just without trying to do anything additional to increase the uniformity of rotation angles that were on the more uniform side of the potential uniformities. Rot sky pause is not the only angle, however, that could be of interest. So the parallactic angle can also matter for weak lensing. So that's the angle between north on the sky and zenith, wherever you happen to be pointing the telescope. And that's important because of differential chromatic refraction acts along the zenith direction. So if you think there may be systematics in differential chromatic, due to differential chromatic refraction, you may want to try and optimize the distribution of the parallactic angle too. And as you can see, the results we get out of minion are quite different here, and that's because rotating the camera has no effect on what the parallactic angle of the observation is. So there's fewer degrees of freedom to help increase the uniformity. And so Phil asked me to provide a figure of merit, and I think 1 minus the angular spread of rot sky pause is a potential figure of merit, at least for the systematics attached to the focal plane systematics. And then there's a few other things we'd like to try. We'd like to look at what are these distributions after, say, just 1 year of observations, and what if we only look at the best seeing data, how uniform is the camera angle in that set of data. And then finally, we'd like to start looking at, can we improve the uniformity of the rotation angles, using one of these strategies. Maybe we can just apply a random dither at the beginning of every night, or at every filter change, or maybe we can even do something more intelligent, a targeted rotator angle, instead of just a random rotator angle, based on the history of what you've already observed. And that's all I got. Thanks.
All right, thanks, Josh. Time for some questions. Harry.
For weak lensing, I can imagine there might be some leverage to taking advantage of really good seeing conditions to spread around, the wealth of good seeing. Have you looked at scenarios like that?
I have not. I believe there are some plans to optimize the choice of filter based on what the predicted seeing may be. Maybe someone else can comment on if that's true or not. But I haven't thought about that in terms of, say, the rotation angle or where you point the telescope, if that particular region hasn't been covered by good seeing, for instance. That's an interesting question.
Timo.
The calculation you described basically a mitigation of systematics, whereas what's Harry's question that goes in the direction of how much statistical power is there compared to, say, can we use better seeing in some filters preferentially than in others, and can we optimize this to get overall not only homogeneity but depth and signal to noise ratio. So I think that would be good to figure out which of the can we spread out this.
Right. So optimizing the statistical power of the survey is an interesting question too. I think the direction we chose to go here was based on the expectation that we'd probably run into systematic limitations before we run out of statistical power. So that was our focus so far. But yes, we could also look at statistical information.
Also, what kind of spatial scales is rotational, metric, because there are different spatial scales that you care about. It doesn't have to be rotationally invariant on really small scales if you don't use it.
So let's see. So we didn't look at this as a function of spatial scale other than to look at the maps. Right, but yeah, that's another thing we could look at.
And in fact, if you remember Humna's presentation, you were looking at power spectrum analysis. So one direction we could go is Josh and Humna could figure out putting those things together. I guess both these points about statistical precision, the answer will matter whether it's in year 1 or year 10.
Right.
And so I think a number of groups are in this boat that with metrics in hand, they can start to ask questions. What will my science look like after the first data release? How long should I wait until I reach a particular accuracy threshold? Ooh, my own duck. Okay, let's thank Josh again. Okay, I hope you, maybe I should turn one of these off. So hopefully you now have a flavor of the kinds of investigations that are going on in this observing strategy community. I hope you can also see what a skilled group of people there are working on this, and you can tell that not only from their slides but also from how they manage to keep on time. So thank you all speakers, this was really good to see. Okay, so what's next? This afternoon in the second breakout session we'll be doing some hacking on the math metrics. So if you're interested in getting involved with this process of investigating the observing strategy, I'd encourage you to come along to that session and just join in with one of the groups that are already doing investigations. We'll have a short tutorial from Peter Joachim about how to put together a metric, and then I think a couple of groups will be trying to use that to extend their analysis. So come along and see what's going on. And otherwise, you can find us anytime at GitHub repository here. Okay, thanks very much, everybody.